This Key Stage 3 presentation is concerned with energy and power, as well as how to draw Sankey diagrams and calculate efficiency, and comes from the topic 8K. Let's understand what power is by looking at this example. We've got two masses which each have a mass of 1 kilogram, and they're going to be raised up into the air by half a meter. The two masses are exactly the same. To do this, it takes the same amount of energy, regardless of how quickly they are raised up in the air. If we time it, the one on the left takes 1 second, but the mass on the right takes 5 seconds. It takes, therefore, less power to raise the mass on the right up into the air than the mass on the left. The equation for power is shown there. Power equals energy over time. As you can see, the time is on the bottom of the equation. Therefore, the smaller the number, the bigger the power. That's why for the masses, the one that only took 1 second is obviously a smaller number than the mass that took 5 seconds, and therefore the one that took 1 second had a higher power. So what is power? Well, it's the amount of energy transferred per second. Now, 1 watt, which is the units of power, is a very small number because 1 joule of energy is a very small amount of energy. And therefore, it's typical to express powers in values of kilowatts, where 1 kilowatt is 1,000 watts, or 1,000 joules transferred every second. Let's look at this example here. We have two identical kettles with the same amount of water, 1 litre in each of them. Each kettle the water has a starting temperature of 15 degrees. Now, we switch them on and time how long it takes before they start boiling. The kettle on the left only takes 2 seconds. That is an incredibly efficient kettle, whilst the kettle on the right takes 5 seconds. Even that is pretty impressive. The amount of energy needed to heat the water from 15 degrees to 100 degrees is the same for both kettles, because the amount of energy depends on the mass of water as well as its starting temperature. However, the power, which we would say the power rating of each kettle, is different. The one on the left, which only took 2 seconds, is more powerful than the one on the right, which took 5 seconds. Now, energy transfers, if we move on, can be shown by drawing what we call a Sankey diagram. And Sankey diagrams are based on probably the most important law in physics, the conservation of energy, which states that energy can only be changed or transferred or stored in different ways. Energy can never be created and it can never be destroyed. This means that the total amount of energy going into a device is equal to the total amount of energy leaving this device. However, the amount leaving could be wasteful forms of energy as well as useful forms of energy. So, how would you draw a Sankey diagram for the following device? The input energy is 100 joules. 80 joules of the input energy goes to a useful form of energy, whilst 20 joules of the input energy is wasted and transferred to the surroundings by heating. Now, when we draw Sankey diagrams, we have to draw them accurately and to scale. And so it's important that you use a sharp pencil, a ruler, and a piece of graph paper. The first thing you need to decide on is a scale. So to make things easy, it's sensible to use easy numbers for your scale. For example, 1 small square equals 1 joule, or 2 joules, or 5 joules, or 10 joules, or 20 joules. As our input energy is 100 joules, in this case, we have chosen 1 little square equaling 10 joules. And so you can see that the width of the start of this arrow is 10 small squares, which equals 100 joules. Now, Going along the arrow, we then draw a downwards arrow. The width of this has to equal 80 joules, but we've stated that one small square equals 10 joules. So rather than 80 squares, it's going to be 8 squares in width. This represents the useful energy. Now in this diagram, it's pointing downwards, but it's often very typical to see in Sankey diagrams the useful energy just going straight forward. We've got 8 squares here, and so we need to have 2 squares here, 2 plus 8 equals 10, to represent the wasted energy. As stated already, the amount of energy going in this case 100 joules, must equal the sum of the amount of energy leaving, 80 plus 20. And so that is what our final Sankey diagram would look like. You then label the arrows, often stating the forms of energy. For example, this could be electrical energy being changed into heat energy and light energy. It's also possible to express the power of a device or the power inputs and outputs. Remembering, power is the energy which is transferred per second. As the time is the same, therefore the amount of energy or the amount of power going into the device must equal the sum of the powers leaving the device. Let's look at another example. In a filament light bulb, 90% of the energy that is transferred to it by heating is transferred to the surroundings by heating. Transferred to it by electricity is transferred to the surroundings by heating. This is wasted energy. So this is a very inefficient light bulb. 90% of the energy is actually wasted as heat, and only 10% is transferred to useful light energy. This is what the Sankey diagram would look like. Rather than giving our values in joules, we're giving the values as a percent. So we can use the same scale that one small square equals 10 joules. Therefore, 10 small squares equals 100 joules, or in this case, I should say 100%. This arrow is now 9 squares to represent 90%, and this arrow here is now 1 square to represent 10%. Again, it's quite common, whether it's in joules or percent, to actually show the useful energy going in this direction from left to right, and the wasted energy percent or power going down. Finally, you label your arrows stating what type of energy the input energy has been transferred to. Finally, let's look at efficiency. Efficiency is a ratio of the useful energy transferred divided by the total energy supplied to a device. It is common to times it by 100, so rather than a ratio or a fraction, we state efficiency as a percentage. Let's try and work out the efficiency in this example here. We've got this light bulb, okay, and we're going to draw a Sankey diagram for it. 40 joules of energy is supplied, but just like in the previous example, only 10%, 4 joules is transferred by light. 36 joules is transferred by heating. If we put those numbers into the equation, useful energy, which is 4, divided by total energy, which is 40, and times it by 100, we get 10%. As expected, the efficiency of this light bulb is 10%. Old-fashioned filament light bulbs used to be very inefficient. Most of the energy that went into them was actually changed into heat, and they had an efficiency typically of only 20 to 30%, whereas new energy efficient light bulbs now have efficiencies of between 50 to 70%. Remember, efficiency can never be more than 100%. That is because the total energy going in cannot be less than the amount of energy coming out. That would break the law of conservation of energy. That concludes this video.